And thanks to all of you for attending this afternoon and not watching basketball, at least for this next hour. So optimization of the activated sludge process requires careful management of three critical parameters. Over the years, wastewater professionals have based their control decisions on measurements from batch tests applied to graph samples or from infrequent laboratory analysis that's measurements done on composite samples for compliance purposes. Today, besides talking about the three things you need to know, we're also going to offer you some alternatives for monitoring that can improve your ability to optimize the process. On the title slide here, we have a couple of pictures to get you in the mood for the talk. On the bottom left panel is a activated sludge system with showing all the three things we're going to talk about. And on the right side is an aeration tank from a local water resource recovery facility. So, taking a look at this cartoon here showing the basic elements of the activated sludge process, the aeration tank, and the final settling tank. There are three things we can do to control this process between these two elements. One is the air, the aeration rate. Another is sludge wasting through waste activated sludge. And the third is sludge recirculation, either through return activated sludge and or internal slicker recycle for nutrient removal. We'll dive into each of these topics a little deeper as we move along. But before we do, I want to introduce a little bit about one of the greatest inventions of the 20th century, that being the activated sludge process. It was spurred by rapid industrialization in the early, late 19th and early 20th century, and had many beneficial effects, especially for public health. Although a gentleman named Ardern and Lockett are generally given credit for invention of the process due to their papers published in 1914, its development was actually the culmination of years of research and discovery. Early on, researchers had discovered that aeration had beneficial effects for odor control, but the treatment ability was less than needed. Other researchers had discovered that the growth of this humus, what they call it was humus, which we might call suspect biological growth, did have some beneficial effects for removal of pollutants from wastewater. But what Ardern and Lockett had discovered was that by retaining the solids in the system and recycling them back into the aeration tank, the solids were said to be activated, and thus the name activated sludge came about. So all configurations are based on this research and invention, and they all have certain things in common. They're biological, microbiological. They are all aerated at some point in the process, where the bacteria or the biology are suspended in the water. And hydraulic retention time does not equal solids retention time. That's a bit of an extension on the findings of Ardern and Lockett. And of course requires specially trained personnel like you folks tuned in today. So let's start with a discussion of aeration. Looking at this chart here, which is kind of a general relation of the ORP on the horizontal axis, we know that we can say that aeration controls the biochemical environment. So, for instance, on the positive side of ORP is where we would have oxic conditions. On the negative, somewhere on the negative side of ORP, we would classify as anaerobic conditions, and then in between is a region we call anoxic. And so depending on what you're trying to accomplish, each of these zones are important. So nitrification, for instance, takes place exclusively within the oxic zone because the bacteria require dissolved oxygen. BOD removal, on the other hand, is done by a lot of microorganisms that can be active under anoxic conditions as well as in oxic conditions. When we start talking about phosphorus removal, phosphorus uptake also can occur oxically and anoxically. But general understanding is denitrification is exclusively in the anoxic portion, or anoxic region of this chart. Moving over to the anaerobic zone then, phosphorus release, again the second part important for biological phosphorus removal occurs in the anaerobic zone. And then fermentation, which is important for sludge treatment but also for biological phosphorus removal, also occurs in this zone. So by managing aeration, you control the environment for the biology. So looking at it a little more specifically, we take a look at this chart which shows reaction rate versus dissolved oxygen concentration. And for nitrification, the curve shown here relates how that rate is related to dissolved oxygen. And it shows that from 0 up to 1, 1.5, 2 milligram per liter DO, an increase in the DO concentration results in a proportional increase in the reaction rate. Beyond 2 milligram per liter, an increase in the DO concentration does not result in an appreciable increase in the reaction rate. And a number we can maybe classify this using this number here, which is the DO concentration at which the nitrification rate is 1/2 of the maximum rate, 0.75 in this case. CBOD removal, the curve for that is shown here with the black line, and this function occurs with at the maximum rate occurring at a DO concentration of 0.3 DO. And so taken together, these curves mean that control of nitrification also ensures BOD removal and establishes the basis for maintaining DO at or below a 2 milligram per liter set point. Diving in a little bit more with dissolved oxygen and performance relating to nitrification and denitrification, this chart shows, again, the max process rate on the vertical axis and the dissolved oxygen concentration on the horizontal axis. The blue line is the nitrification rate. Again, it should look pretty familiar. It's very similar to the last chart. And so it increases with DO concentration. But the magenta line, which is the denitrification rate, is new to this chart, and it shows that a higher dissolved oxygen concentration actually reduces the denitrification rate. So by maintaining too high of a DO concentration, you can also compromise denitrification. From an energy perspective then, other incentives for minimizing DO concentration are shown by this chart, which shows again the DO concentration on the horizontal axis, the cost on the vertical axis. On the left side is a cost multiplier. So for instance, for the DO curve here in red, at 2 milligram per liter, there would be no additional cost to provide that oxygen to maintain that 2 milligram per liter. So your multiplier is 1. But for instance, if we were to maintain DO at 4.5 milligram per liter instead, it would result in, relatively speaking, a 1.5 times increase in cost to provide aeration for the activated sludge process. And in extreme cases, say for DO concentration of 8, that cost is over 4 times as great as the cost it would be to maintain a DO of 2 concentration. So very significant impacts of not controlling dissolved oxygen. I did promise we would talk about dissolved oxygen measurement and ways to control the process, alternative ways to control the process. The method here, ASTM, defines a means for measuring DO with an optical method. And it has a lot of advantages over the traditional membrane-style polarographic dissolved oxygen measurement. Very stable calibration, lower maintenance. There are no membranes to replace, no electrolyte to replenish, no sulfide interference, and a very good accuracy. So these are all improvements over the polarographic style of measurement. On the right-hand panel then is an example of a continuous online dissolved oxygen sensor. See, there is a light source on the inside that reacts with a fluorescence layer on the underside of this removable, replaceable sensor cap. And that reaction establishes the relationship between a fluorescence, for example, and dissolved oxygen concentration. This sensor is digital such that the calibration constants can be uploaded to the system through this chip built into the sensor cap. Now, for portable or benchtop applications, there are other benefits of optical DO. One of those is no stirring requirement and no warm-up requirement. So for spot sampling, for example, optical DO is just as applicable as it is for online process monitoring. ORP is another way, important measurement that you can use to help control aeration. Some have referred to it as a DO sensor that's able to measure negative DO. But that aside, just looking at the technology itself, we've got 2 electrodes connected between the sample through a voltmeter and a reference electrode with a junction and a measuring electrode, an YSI, with a membrane. The difference in millivolts between these 2 electrodes then establishes what the oxidation reduction potential is, and it could be positive or negative. Again, there are continuous and spot sampling applications for ORP measurement. The continuous probe shown on the bottom right and very easily incorporated into a spot sampling instrument as well. So moving on to the second topic, second of the 3 things, we'll talk more about sludge wasting. Sludge wasting controls how much biomass is in your system. And there are several approaches to sludge wasting. Settlability is one common usage, and the picture here shows diluted samples of mixed liquor, 100%, 50%, 25%. And by comparing these results, a professional can decide whether or not additional or less wasting is needed. Other strategies are to maintain a constant mixed liquor suspended solids. Again, with grab samples, you can measure these samples in your lab with the analytical balance shown in the picture there. Centrifuge spin is another common method, and really the spin is actually very versatile. Because it can, by measuring samples of the mixed liquor, the return activated sludge, and the clarifier at once, you can get an idea of the mass balance and also decide whether you need to waste or whether you need to change your RAS rate. But all of these methods have the drawback that they're batch samples and can only be done when the operator is available or has the time to do them. Of course, the same is true of F to M in solids retention time if For instance, you're taking grab samples or spot sampling with the handheld shown in the picture. But I want to talk more about solids retention time in the subsequent slides here, and how it can be a continuous monitoring process. So we have another cartoon here showing, again, an aeration tank and a clarifier linked by the return activated sludge. And when we talk about sludge age or MCRT or SRT or CRT, they are all different calculations, but in essence, they are the difference between the biomass entering the system and the biomass in the system divided by the biomass entering or leaving the system. And to define an SRT calculation as the inventory over the wastage, we have, so you could, for a given SRT set point, neglecting the effluent total suspended solids, calculating the volume of a aeration basin, measuring the mixed liquor suspended solids concentration, measuring the return activated sludge concentration, you can then directly calculate the sludge wasting rate needed with this formula. Of course, this is very easy to do with online measurement with, for instance, a suspended solid sensor in the aeration tank and an insertion style suspended solid sensor in the return activated sludge line. So what should be the target SRT? Well, it depends on your treatment requirements, and I'm going to give you some general guidelines here. And so as the number of functions increase, the target SRT has to increase. So for instance, with DOD removal only required, you would have a lower SRT requirement than you would for COD removal and nitrification, and that would be lower still than what would be needed for DOD removal, nitrification, and denitrification, and up to a maximum of COD removal plus nitrification, denitrification, and biological phosphorus removal. So let me offer an example of nitrification design. This chart here shows nitrification SRT versus temperature on the horizontal axis. And the line there is a plot of an equation that defines that relationship so that the minimum SRT for your system depends on temperature. For instance, between 20 and 12 degrees C, which might be typical wastewater temperatures. Of course, that being the minimum SRT, we want to make sure we give ourselves a safety factor. So a design could be based on something, a safety factor, for example, 1.5. And so we would be able to control nitrification by maintaining our SRT between 6 days at 20 degrees Celsius and 12 days at 12 degrees Celsius. There are some trade-offs, though, to maintaining that higher SRT, so that there is a need to limit that SRT to the maximum extent possible. So if we look at this chart here, it shows ammonia removal efficiency versus sludge age. And so a higher number is better. And in this case, in the blue area here, we have inadequate ammonia removal. And in the red area here, we have ammonia removal but excessive sludge age, leading to higher power consumption. And so the optimum sludge age is somewhere in between that allows you to achieve nitrification without excessive energy consumption. Now, besides nitrification, SRT has effects on a lot of other parameters. So for instance, looking at this chart of effluent TSS on the vertical versus over 1 year of data. And the arrow here indicates where this facility implemented SRT control. And very plainly you can see that prior to the arrow, the effluent TSS is higher and more variable, and after SRT control is implemented, more stable and lower values. When it comes to solids measurement then, of course the gold standard is the laboratory gravimetric technique, but for faster measurements there are optical ways of measuring solids, and there's a couple technologies. Vivate reflectance or absorbance. The measurements are fast and simple, which is very desirable. But if you have an online instrument, it is also factory calibrated and low maintenance with integrated cleaning systems. So for example, with the Ultra Clean technology, which is on this TSS probe shown here. Spot sampling is also very commonly done, and it can be done with a handheld like this one shown here. But one caution I want to offer is that the TSS, the spot sampling sensor, is generally not factory calibrated, and so needs to be calibrated in the lab before taking it out to the basin. So especially when you're verifying measurements, you want to have a properly calibrated handheld sensor. Okay, we're up to 3 of 3, and that is sludge recirculation. So one reason for sludge recirculation is to control biomass distribution, and RAS flow is critical to clarifier performance. There are a couple of methods that are implemented. One of them is constant flow method, and in this method you set the RAS flow rate manually. It's basically open loop control, and only changes when you go to make the change. A feed-forward control of controlling RAS flow is to set it proportional to the wastewater flow. So for example, 50% of the forward wastewater flow. The drawback to constant percentage is that you'll get the highest loading, clarifier loading, at the highest flows, so really at the worst possible moment. But constant flow, on the other hand, is most applicable then to smaller facilities. Now, whichever method you're using, flow rate control can be based on a number of different approaches. I'm going to talk about one approach, the sludge blanket depth approach, and this diagram shows again a clarifier with the wastewater flow plus the RAS flow coming in and the RAS flow and the effluent flow going out. On the right-hand panel is a flux curve. Forgive me, this will be something that's more familiar to engineers, but it's a very simple principle to understand. And the idea is that this flux curve defines the quality of your sludge. And the idea is to maintain your operation below the curve. So let's look at an example. If we plot wastewater flow and RAS flow on the chart, the intersection of those lines is our mixed liquor suspended solids concentration. In this example, that RAS flow line is outside of the curve, and the result is that sludge will accumulate and the blanket will rise. In a worst case situation, that biomass would continue to accumulate and the sludge would overflow the weirs and you'd have solids washout. But even if that part is avoided, the drawback to this allowing that to happen is that the mixed liquor suspended solids concentration is reduced. So looking at another approach is to increase the RAS flow rate. By increasing the RAS flow rate, both flow lines and the state point, the magenta dot there are maintained within the curve. For sludge blanket depth measurement, there are a couple of options. On the left-hand side is a visual measurement, which I'm sure many of you are familiar with. It's a sludge judge. And basically it's a core sample that you put into the clarifier and pull it out and read how deep the sludge is. On the right-hand panel is a instrument for doing that. And this instrument uses sound waves, so it's acoustic. And basically it's measuring the echo from the sound waves hitting the sludge below. With the visual and the acoustic methods, they should generally give very similar results, but under certain circumstances, for instance, when the sludge blanket is not very well defined, you can get a very subjective evaluation on the sludge judge and may or may not agree with your online blanket level sensor. Sludge recirculation for control of denitrification is the other important thing. Nitrate is the critical measurement in this case, and the diagram here is a denitrification configuration, and so the optimal location for nitrate sensors in this is to have a nitrate sensor at the end of the anoxic basin and a nitrate sensor at the end of the aerobic or oxic basin. And taken together, the measurements from this can help you to meet the three objectives for denitrification, and that is meeting nitrogen limits, of course, maximizing the use of wastewater COD, and minimizing the external carbon dosage, which is very expensive. For nitrate measurement, there are also ISEs for that. So again, a potentiometric method where difference in potential between a measuring electrode, an ISE, and a reference electrode are measured, and these are then correlated to an ammonium or nitrate concentration. And the benefits of newer technology are that multiple electrodes can be fit on this probe, so you can measure ammonium and nitrate simultaneously, and also compensate with a potassium or chloride probe. They are reagentless, have a stable calibration, electrodes are replaceable, and there's a large measuring range. This is also possible with a spot sampling instrument. The digital sampling system shown in this picture then also can be outfitted with ammonium, nitrate, and even DO probes to measure those parameters simultaneously. I want to offer another way to measure nitrate, though. ISEs do have electrodes that need replaced from time to time and are not factory calibrated. An optical method for nitrate monitoring is shown here. Basically, it works by measuring the absorbance in the ultraviolet range. Nitrate absorbs ultraviolet light. Two different versions are offered, a multi-wavelength spectral instrument, which is factory calibrated, or a single wavelength instrument, which requires a user correlation. The picture on the right side then is an online instrument in the mixed liquor, and the inset there shows the measuring gap where the measurement happens, and it also can be outfitted with integrated cleaning system. So to summarize today's webinar and talk about future webinar topics, process control, it is easier than you think. It is a matter of using aeration to control the environment, sludge wasting to control the total biomass, and sludge recirculation to control biomass distribution. Well, I'm done with the prepared talk for now. I hope you have been getting a lot of questions posted because we have some time to answer a few. Thanks again for your attention.
Great, thanks, Rob. I do have some questions coming in. One of them is dealing with access to the slides and the recording. So in 2 days, we'll send you guys an email with a link to the recording, and then we'll post the slides themselves on a website called SlideShare, and that'll be as a PDF. So the slides will be available as a PDF on our SlideShare page. Some other questions for you, Rob? What is a target blanket thickness we should strive for in our secondary clarifiers?
Wow, you guys are really starting off with the tough questions. This is really, there are this is really a philosophical discussion, as many things in wastewater treatment are. There are those out there that advocate maintaining a minimum sludge blanket. It makes some sense to me. But I think the most important thing is to do what works for your system the best, and maybe to prevent the sludge blanket from getting too deep or deeper than you can manage.
I like philosophical debates about wastewater. Another question for you, Rob. We keep high DOs to prevent denitrification from lifting the sludge in our clarifier. What else can be done for this problem?
Yeah, when I've been out and around, I've heard this a lot when I talk about this subject, and you know, I mentioned, I tell people that you should always maintain minimum DOs, and 2 is enough, and then they'll say, well, if we keep that low of a DO, we'll be popping sludge out of our clarifier, and that is a genuine problem. So a couple things you could do, again, if it's within your capabilities there, your equipment and such, is maintain minimum sludge blankets. I guess so. This nice little follow-on question to the previous question. But also, if you have the capability, maybe do some denitrification in the front end of the aeration tank with maybe an oxic tank. I know some of our customers have taken that task on themselves. They basically built a small anoxic zone into their aeration tank, and it's worked out really well for them.
Okay, thanks, Rob. Next question. Can nitrate measurement also be used for aeration control?
That's another very good question, and it can be. I mean, obviously, your nitrate is a product of nitrification, so as ammonium goes down, nitrate goes up. But more commonly, it is the ammonium that's measured for aeration control, so that for instance, as the ammonium concentration goes up, the aeration rate increases, and when your ammonium concentration goes down, the aeration rate decreases. But I suppose maybe the opposite could be used to control aeration via nitrate measurement. Good question.
The next question deals with instrumentation.
Sorry about that. The next question deals with instrumentation. How reliable are the probes, and how does an operator know when results are drifting?
Well, reliability is reliability is good. I mean, compared to the traditional styles, especially with let's talk about dissolved oxygen. With dissolved oxygen, for instance, an online sensor, a calibration can last for 2 years. So there you've taken the calibration out of the equation. But also as far as maintenance goes and cleaning, no longer are we talking about replacing membranes and such. You really just have to clean off the sensor cap or the sensing element so that oxygen can interact freely with that fluorescence layer behind the sensor cap. But really, at the end of the day, the reliability is going to depend on how good a care the owner takes of the instrumentation. So a sensor that's neglected, no matter how well designed, is eventually going to give poor data. So no matter what, manual cleaning is going to be an important part of reliability.
Yes, keep them clean and clean them often. Question for you, Rob. How does excessive sludge age increase energy costs?
Yeah, this starts to get into a bit of a philosophical discussion as well, but I'm going to start with where I was coming from with that chart was that so basically when you've got bacteria in the system, they're living, they're dying, and so you have an oxygen demand from the living part. They're consuming organic matter, they're consuming ammonium, but the dying part as well. So when these bacteria die, their parts become available for the other bacteria to then cannibalize. So it's kind of it's been referred to as cryptic growth because it's happening in the system, but it's kind of hidden from the observer. However, I think there are arguments out there to be said for maintaining higher SRTs than lower, but I think from our point of view today, it should be to optimize that solids retention time.
How often should SRT be controlled?
Good follow-on question. And that is also difficult to answer, but I will say from our experiences with our customers, a lot of utilities are very reluctant, for example, to automate their SRT control, and the concern is that they'll waste too much or waste too fast or whatever, and that is a concern. But generally, if you are automating SRT control, you want it to be very slow, and so, for example, you want to take an average of many measurement points, maybe even days worth of data, in order to track your SRT. However, I do know there are utilities that update their SRT set points on 15-minute intervals, and they have success with it. I think the important part, regardless, is having transparency in the system so you can see when there are problems and act on them when needed. And, of course, keeping the sensors clean.
We are getting a lot of questions coming in, so I appreciate that. We'll try to get to them. Staying on SRT, how does SRT control improve TSS?
Yeah, I was waiting for somebody to ask that question. And so, really, it's a matter of controlling the sludge quality. And again, this can get into the philosophical range as well. But here's my understanding, and you may disagree or comment. But the sludge quality is really what affects the settleability of the sludge. And by say, for example, not controlling SRT, that sludge quality, the properties of the biomass can vary. For example, the settleability, flocculation rate, compaction rate. By maintaining an SRT, you find an SRT that works, and you keep your system at that SRT to keep it functioning properly. Good question.
Yes, again, staying on the subject of sludge retention time, you showed a chart for target SRTs, and with, I guess, long winter we've all had, do you know what the target should be if our average temp is 10 degrees Celsius or less?
Yeah, thanks for the question. Well, it's going to depend on what you have to do. So if you have to do nitrification, for example, going back to the chart we showed earlier, the target SRT would be more than 12 days, and I think that's pretty much in line with a lot of utilities. If you do not have to do nitrification, though, much lower SRT could help you to achieve your goals and reduce your energy consumption and maybe even the number of reactors you have online. Good question. Thank you.
Going into instrumentation questions, how frequently do wastewater treatment plants recalibrate their TSS inline sensor? Since calibration is dependent on sludge, readings will change, and will the TSS need recalibration?
Well, there's a lot of different approaches to this. As I mentioned, an online TSS sensor can be factory calibrated. So if your mixed liquor properties are similar to what's in the factory calibration, you plug it in, and you go. Recalibration intervals then would have to do with one, whether your sludge changes, and that may happen seasonally. So, for instance, you might need a recalibration for winter and summer conditions. But also, of course, with age, the sensor optics are going to age a little bit, and of course that's going to be a much slower process, but you'll know when you're drifting apart by keeping a good record of verification measurements with, for example, a calibrated handheld or good graph samples measured with good laboratory practice in the lab. And that's how you'll know when it's time to calibrate your TSS sensor. And one other important thing, I guess, is your tolerance for inaccuracy. I think 100 milligram per liter will be important to some and not so important to others. So really, your expectations also define what that interval needs to be. Thanks for the question.
One more instrumentation question. We have DO probes installed at the beginning of the aeration basins. Should they be moved to the end of the aeration basin?
Another terrific question, and one that, again, will have differing responses. But so I think it depends, again, on your control system. It would be my desire to have the sensor located where you can make controls. So, for example, if you're controlling based on a drop leg at the front end of the aeration basin, monitoring at the front end is probably appropriate. On the other hand, if you're monitoring at the back end of the concentration, if you're monitoring at the back end of the aeration basin, the influent loadings can change, and when they change, the DO concentration, DO could be consumed at the front end, and you wouldn't notice it at the back end until several hours later when the water makes it to the end of the basin. So that's kind of my 2 cents, but yeah, there's a lot of things to think about when you're controlling dissolved oxygen.
Next question. With phosphorus removal becoming more and more important to our area, how does DO concentration affect phosphorus removal?
Thanks for the question. Yeah, so I think early on I had a chart there that showed that, well, first of all, let's talk about phosphorus removal. Let's talk about biological phosphorus removal. It requires P release, and it requires P uptake. So from that chart we showed early on, we showed that P release occurs in the anaerobic region. And so by controlling DO to, obviously you want DO to be 0 or near 0 in that region in order to have proper phosphorus release. At the other side of that then is phosphorus uptake, and that occurs under oxic conditions. Now this may violate the 2 milligram per liter set point that I mentioned earlier, but it may be an exception. At the front end of that aeration tank, the general consensus is that you want the DO concentration to be not limiting so that you get the maximum phosphate uptake. And in that case, it may be desirable to have a higher DO than 2 milligram per liter. When it comes to chemical phosphorus removal, which we haven't talked about much today, I think the DO concentration is a little harder to establish a relationship. It's probably going to be that the DO concentration is going to be controlled by other processes. But good question. Thank you.
This stays along that topic for phosphorus removal. Which measurements can be applied to phosphorus removal?
Yeah, it's a good follow-on question. A number of utilities have used ORP very effectively, especially in batch-type processes. But the real gold standard would be orthophosphate measurement. The orthophosphate gives you an indication of phosphate release and also phosphate uptake. Of course, total phosphate, or TP, is usually the compliance parameter, but that parameter is really a function of how well your separation device is working. So, for example, your final clarifier or your filter. And for controlling those, you would want to use sludge blanket level and TSS to make sure that that particulate phosphorus is captured and doesn't escape into the effluent. Well, I guess those are really the main measurements that are applicable to PE removal. Good question. Thanks.
We are changing topics to return activated sludge flow. Should RAS flow always be increased to offset a rising blanket?
Thanks. Good question. I love it when people are looking at the charts and saying, hey, wait a minute, that doesn't make sense to me all the time. What if this happens? And so the question is, in general, yes, but you also have to consider that your sludge blankets may be increasing because your SRT is too high. So a response to the rising sludge blanket may also include increasing the wasting rate. And so, for example, I mentioned that centrifuge spin control test. One of the neat things about that, although it's a batch test and we don't sell centrifuges, if that's what you got, I mean, it can give you the information you need so you know whether you need RAS control or waste control. But thanks for the question.
How is nitrate monitoring related to carbon?
Yeah, I guess I kind of skipped over that a little bit in the interest of time. I want to say at this point, if I didn't already, that we're going to have separate webinars on each of these topics where we'll get into each of these in more depth. But to answer your question, with denitrification, really there's two conditions. One is you could either be nitrate limited, in which case there's not enough nitrate, or carbon limited, in which case there's not enough carbon. And so measuring that nitrate tells you which condition you're under. If you're nitrate limited, for instance, in the anoxic zone, the response is to increase the recirculation rate. On the other hand, if you're carbon limited, increasing the recirculation rate may not improve performance. So you need to know what that nitrate concentration is.
We have a few minutes, so we still have questions coming in. Going back to calibration, Annually, we zero calibrate our solids probes. Is calibrating so far outside our range of operation a good practice? Is it possible or a better practice to calibrate within a known concentration?
So the question is it better to calibrate with a standard solution than in the process?
What's the best calibration? They annually zero it? Is that a good practice? Or should they calibrate closer to their measurement range?
Okay, thank you. Well, I mean, that kind of depends on your instrument. So, for instance, I know with the handheld I showed that that's one of the methods of calibrating it is a zero calibration. But for the continuous measurement we showed in the slide there, I think it's the zero really is unless you happen to be measuring in the effluent, the zero is not that important. You really would probably benefit by calibrating within your normal operating range. So if zero is near your normal operating range, then yes. But otherwise, I would say probably not. Thank you.
All right. Next question. This goes back to the graph that you showed the flux curve on. Can you explain briefly again what the flux curve represents when discussing mixed liquids, blended solids, and raspberry?
Terrific question. Yeah. So that curve really represents the quality of the sludge. It's actually very easy to generate, and I would encourage you to do so. Really all you need is a settling column and take some measurements over time. And it's defined very well in a WRF protocol. But so that flux curve then defines how well the sludge settles. So what is the quality of the sludge? And so it gives you a region over where you know. Basically, it gives you a mass balance. It gives you a way to instantaneously calculate your mass balance because within that curve, by plotting the flow rates for any condition, you can know under what condition you're operating. So, for example, the example I gave was thickening failure, where that RAS flow rate curve is outside of the flux curve. Well, let's take the extreme example. If we had plotted those two lines and that point, that intersection had fallen above the curve, so outside the curve, that is a very serious condition. That's clarification failure, and basically all your clarifiers just become a white spot in the line. It's a complicated topic. I hope I've helped to answer that a little bit. But I'd be happy to address it offline with anybody that's interested. Thanks.
Some of the remaining questions are pretty process specific, and we might need to take them offline. Here's one more that I'm going to toss over to Rob. What is the desired retention time in an anoxic zone?
Good question. Again, that depends on what you're trying to achieve. So for denitrification, I think it's not uncommon for that anoxic zone volume to be up to 40% of the overall aeration tank volume. Could be less. And a lot of it depends on how you're operating the system. So for example, let's take the case where, this is a perfect question. Let's take the case where you're operating your oxic zone at 6 milligram per liter. And when it leaves the clarifier, you're still at 4 milligram per liter. So that return activated sludge is going back to the anoxic zone with 4 parts per million of dissolved oxygen. That is going to eat up your anoxic zone volume, if you will. So you're essentially losing anoxic zone volume by putting that high DO RAS back into the anoxic zone. So to minimize the volume, you want to have minimize the dissolved oxygen concentration, minimize the nitrates, and minimize oxygen from other sources. But yeah, that really dovetailed nicely with some of the other topics. Good question.
That brings us to 2:30 Eastern Time. So I want to thank you guys for joining us today. I want to thank Dr. Rob for his excellent presentation. Please fill out the exit survey on your way out and contact us if you need any more information.